Last time, what were we doing? Particle on a sphere. We came up with our model system. We got to a point where we said our wave function depended only on theta and phi. And then what were we trying to do after that? Find a wave function, and also, what about our wave function were we trying to show? Yeah, it's separable. So it could be separated into two different components, let's say, and that those components were separable. And we arrived at this equation. I believe. Staring at it for a second. Yeah, let's just write all this crap down. I'm going to be lazy and leave off some of the dependent variables. Are you guys okay with that? Okay. We ended up with 1 over sine squared theta integral phi squared. We had big theta, big phi. Partial of theta, sine theta, partial of theta again, big theta, big phi, like that, right? Okay. What did we say about these partial differentials, though? Yeah, they only affect one of the components. So this guy, that differential, what's the only thing it influences? Yep, that guy. And then this one, and eventually this one. Yeah. So how could we rewrite this equation? What could we pull out from this guy? Or this red term? And what could we pull out from the blue term? Yep. So we can just pull theta out of this guy. And then what about that one? Because basically to those partial differentials, these guys are constants, right? Okay. However, we still got to separate this stuff. So what would you do next? Yep. Divide through by these guys, right? Okay, what's going to happen with these two? Yeah. 1, 1. Okay, so let's rewrite that and see what that looks like. Okay, negative epsilon is equal to 1 over b, oops, theta over big theta like that, right? Okay, what else would we do? What things are changing here again? B and theta. You spot anywhere here where we have those two variables next to one another? Yeah. This is the problem child right now. What are we going to do to get around that? What do you think, Will?
You said what you said before.
Yep. So this term has theta in it, but really we only want it to depend on phi. So mathematically, what could we do to get rid of this guy? Or at least remove it from that term. Because right now, this thing depends on both theta and phi. What does this blue term only depend on? Just theta. So that one's good to go. This guy isn't because it has both of them. So what are we going to do? Yeah. We multiply by sine squared theta. We have to do it to everything in here. So we get negative e sine squared theta is equal to 1 over phi plus, the order in which I put this is important. We're going to pull that out front. So we're going to multiply sine squared theta. We already have a 1 over sine squared. They're going to cancel out, so we're going to be left over with sine theta, big theta, partial theta, like that. Okay. We're almost to a point where we have a solvable differential equation. What do we got to do next? Or what do we usually do when we want to have a solvable differential equation? What do we try to get one side of the equation to equal? We could. That's tough to do. What about when you have something like what do you do there? Yeah. These are easy differential equations, or can be thought of sort of as differential equations. We set one side equal to 0. What side do you want to set equal to 0? That's what I would do too. So we're going to move that over. And we get just that p term, that's all equal to 0, plus all of that junk partial of theta oops. And then the sign just changes like that. Okay. What was the benefit of doing all that, or what was the purpose of doing all of this arrangement? How many terms do we really have? We have 3. What does this guy depend on? Yep. This term. Finally, that last bit. Yeah. Have we separated all of our variables apart from one another? Yeah, we have. We have terms that depend on only one variable. So we derived a situation where they are separable, which is good, because now we can use the skills that we learned in differential equations to solve these things. However, I highly doubt you covered the solution to this specific thing. People spend a lot of time looking at the mathematics of it. This guy you already know. Where did we do this one? Yeah, this comes from, the solutions to this portion come from particle in a ring. These guys come from Lagrange functions, which we'll talk about in a minute. The other thing is, we know that these two depend on one another. So if we know one, we can get the solution to the other. What does this stuff, what quantum number does this one depend on? Yep, m sub l. So from differential equations, we know that these terms are equal to constants, m sub l squared, and are connected. Now, how did someone prove that? That takes way more time than we have to go through. But basically, if we take that portion and solve, we know that this, these two things multiplied by one another gives us negative ml squared. And we solved this one already. Now, when you said particle on a ring is where we solved that one. the wave function, or the portion of the wave function that depends on phi. What is the wave function for that one? Times e to the what? Yep. Yep. So cool, we can use that one already. The theta portion. That's where we're just going to say, poof, magical math. It falls out of the Lagrange functions. So, theta solutions. I don't know that that's how you spell or say Lagrange, but I've always called it that way. Did you guys ever talk about those at all or no? Okay. There are a series of solutions that are well known to mathematicians because there's a relationship there. It pops up in a certain set situation. So this is well known to mathematicians. Or at least the ones that study this sort of junk. Okay. However, there's a relationship that happens between these two sets, or these terms, that has restrictions. So let's talk about the restrictions. What are the only possible values of phi that we can have? Or what's the max and what's the min? So particle on a ring. What's the smallest number of radians we could have? 0. Yep. To what's the maximum? Yeah. At least that's where it's unique. The other thing is we have our system like this. So if we're talking about phi, we're talking about the red circle, right? Theta is the white. Where must the wave function match? So if we say theta, I don't know, starts at this pole. Yeah, so actually pi, right? Is that right? For half of a circle? So at the poles, this portion of the function has to match this wave function, right, for it to be continuous. And then up here, if you're on this side, it has to match that side as you get really, really close to those poles. There's weird stuff that happens at those poles, but. So the wave function has to match over the poles. The restrictions of this guy and the requirement the wave function to match over the poles, be continuous. It introduces another quantum number. We talked about 4 quantum numbers in Gen Chem, and you probably talked about 4 in inorganic. What's this quantum number? Yep. It's L. So some requirements of L. Based upon these restrictions that we put down. L must be positive. Okay, let's review quantum numbers real quick. What are the 4 quantum numbers we can have? You don't have to write this down, by the way. N and M sub s are the easiest to deal with. What's the rules for N and M sub s? Yeah. Gotta love fermions for that reason. What about N? Yep. Yep. And what's the rule for it? Yeah, any positive integer, so 1, 2, blah, 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 blah. What's the rule for L? Yep. The rule for ML? Yep. Okay, L depends on N, right? Or is restricted by that, but what about these two? Yeah, they sort of depend on each other. If you know this one, you can know that one. Even if you know this L, you don't quite know your N value. But these two are connected, and that's an important point. M sub L and L are connected. And then you already told me what the rules for ML are, but just reiterate them again. Yeah. Okay, so we have a new quantum number. Now the solutions to what we have, if you combined the phi and the theta term, you get what are known as the spherical harmonics. The sheet I gave you guys last time, do you have that nearby? Let's talk about the solutions to those. And what they mean. So rather than have you solve the solutions for theta, it's kind of given to you on this sheet for you. If you notice, what 2 parameters do you have to know? Yep, you have to know L and M sub L. These are normalized. So the stuff you see there is already normalized. You do not need to factor in a normalization constant. And it can be represented in 2 different ways. You might see psi, depending on these. Or what's another way we could represent these spherical harmonics? Or what do you see on that table? They give you the symbol Y. What other things are indicated there? Little subscript. If you can read it, sorry, it's probably. Yeah. L and M sub L. And then it also depends on theta and phi. So you'll see them represented either way. Most of the time, the spherical harmonics are represented with a Y. The functions must satisfy. Negative L plus 1. So that has to be true for them. So that's just another restriction that gets placed on them, okay? Are there any questions about that right now? Again, what two quantum numbers do you have to know in order to figure out what your wave function looks like? Yep. Yep, you got to get L and M sub L, okay? You can see on here, if you wanted to split those terms apart, you have the phi term and you have the theta term if you need it. But most of the time, you're just going to be using the spherical harmonic functions, okay? All right. Let's draw some pictures and let's look at some animations. And then we'll be done for the day. How does that sound? Oops, if I can sign in correctly. So let's draw what these functions look like. Am I okay to erase this side? So, question, what do functions look like? We're going to look at L is equal to 0. If L is equal to 0, what's the only possible value of ML? Yeah. Let's look at L is equal to 1. What's a possible value of ML we could have? Yep, could have 1, negative 1. What else? I want to do 0. We could have an L value that's equal to 2. What are the possible values of ML? 0. That's the one I want. What else could we have? Yep, plus or minus 1 or plus or minus 2. Let's see. Oh yeah, there we go. That's a cool one I want. But we're going to look at M sub L is equal to 0. Then we'll have L is equal to 1. M sub L is equal to plus or minus 1. L is equal to 2. ML is equal to plus or minus 1. And we'll leave it at that for now. There we go. Sorry, I'm finding cool animations over here. It's not the one I want, though. Okay. L is equal to 0. ml is equal to 0, look at your table. What does that look like it's the solution to? Or what do you notice about that function? Yeah, it's just a constant. So what does that mean about the sign of the wave function here? Positive, negative? Are there nodes? Yeah, it's all positive. Are there any nodes? No, no nodes. Let's look at L is equal to 1, ML is equal to 0. What is the only parameter that's factored in or is considered with that wave function? Theta. Which way is theta? Is theta this way or chopping the sphere in half? Okay, so what that means is there's going to be a sign change in which direction? Will there be a sign change anywhere along the horizontal? No, but there will be along here, right? Depending on how you define it, we get positive along here. I'm going to color it in the best I can. And negative along that side. Let's look at L is equal to 2, ML is equal to 0. Again, what is the only dependent variable we have? Just theta again. So what does that mean? Where's the sign change going to occur again? Yeah, along that way. And I'm going to try my best to draw this. Kind of down the middle. We have negative, positive, positive. So we've introduced a new set of nodes. Okay, let's look at L is equal to 1, ML is equal to plus or minus 1. What do you notice about that guy? Oh, there. No. So it's going to have a combination of the two, right? So there's a portion that gets cut in half. I'll try to draw it kind of along here, where one side will be negative, one side will be positive. What about L is equal to 2, ML is equal to plus or minus 1? Yep. So it's going to cut in two directions. This is going to look somewhat complicated. I'll try to color that a little better. So negative, positive, negative, positive, negative, positive. Okay, these pictures probably don't help out a ton. Let's look at an animation to see what do they actually look like. Then we'll be done for the day. I want to find a good one though. Oh man, that is not what I want. I know the exact one I want. Now I'll try this guy. Yes, that's what I want. There we go. I found it. Hooray! I know I can tell you guys are just as excited about these, but it's going to be cool. They blip. If this thing ever turns on. Oh, come on. There we go. So you can keep track of what they're calling M is the M sub L value. What they're calling N here is actually our L values. So if you consider N is equal to 0, or excuse me, L is equal to 0, ML is equal to 0, it was all the same sign. These things can switch phases, whether it be positive or negative, or how you define positive or negative. But you can see if we consider a system where we're just increasing our L value, we keep on adding nodes along this direction of the poles. As we start adding M sub L values, we start introducing nodes along not only the horizontal, but also the vertical. Does that make sense? Okay, I know it's kind of like a squint, but if you had to match these to atomic orbitals, remember, atomic orbitals or the distance away from the center, the nucleus impacts things. What type of atomic orbital does that look like? These guys, what do they look like? These ones, what do they look like? D. These are just the angular parts to the atomic orbitals. We have to include R to get those cool dumbbell shapes, to get those cool butterflies. And then when we start talking about like F orbitals, the butterflies on crack, to get those, you gotta consider R. So that's where we're gonna head next, is let's talk about including a system where we can vary that R distance. Okay? That's all I have for you guys today. Are there any questions right now?